Hello, this video is how do you form half equations electrolysis edition. Very exciting addition for you. We're going to go through, we won't do an electrolysis recap on this video. That is on another video on my channel for you to have a look at. We are going to just look at half equations from an electrolysis perspective. I do have another half equations video that you might want to watch before this one. Let's start off with, really quickly, I feel like I say this word all the time, ionic compounds. Ionic compounds are what are split up using electricity in electrolysis. Now, why I'm talking about ionic compounds is because they are made up of ions, and these ions are relevant because it's the ions that you write into these ionic equations. Now, you will be familiar with the fact that ionic compounds can either be molten or they can be in solution. Okay, now when they are molten, i.e. they have just been melted, they will have two ions in them. Okay, now when they are in solution, i.e. they have been dissolved in water, there will actually be four ions at play. Now the reason I'm talking about this and the reason why it's so important is that a half equation, again like I've said in my other videos, a half equation is describing what is happening to a species of ions at any one time. Now in electrolysis, all a half equation does in electrolysis is describes what is happening to the ions that have gone to the electrode. So when you have two ions in a molten compound, that's nice and easy, two ions, two electrodes. However, when you get to a ionic compound that is in solution or dissolved, you've got four ions, and we have to look at the effect of water. So I'm really quickly, this is something that you should be practicing, and I've said for my students to practice before, is that what you should be able to do before you kind of really get stuck into electrolysis questions, you should be able to just identify and split up compounds into their ions, so like sodium, Na+, chloride, Cl-. So I've said that you should practice that using your common ion sheet. Now that's fine for sodium chloride, because like I said, when it's molten, there's two ions, nice and easy. Now, when you get to a solution, not only do you have the two from sodium chloride in this example, you have also got two ions from the solution part. Now, the solution part, as I've said, is just water. Well, water has its own ions. It has a H+ or has H+ ions in it. It also has OH- ions in it, four ions at play, like I said. So we've now got to decide. So molten sodium chloride, molten compounds, nice and easy, two ions, two electrodes. And you can do two half equations for it. But when you look at the solutions, you now must decide which ions go to which electrode. Now, I've got the rules. There's two rules that you need to know. The rules are on my next slide, but I'm just going to talk you through it while I have these ions in front of me. So let's start with the positive ions. So we have two positive ions here, Na+ and H+. Now the rule is that if there are two positive ions present, the least reactive ion will be discharged at the electrode. Now, discharged at the electrode just means that it goes to the electrode, it loses or gains electrons, and it's produced. So again, that rule is if there are two positive ions present, the least reactive of the two will appear at the electrode. Now, sodium is a group 1 metal, very reactive. It is far more reactive than hydrogen. So it is going to be hydrogen that appears at the negative electrode, and thus hydrogen that you will write a half equation for. Now, the second rule looks at the negative ions, Cl-, OH-, or the hydroxide ion. Now, the rule is if there are two negative ions present and one of them is a halogen, the halogen will be discharged at the electrode. Remember, discharged means it goes to the electrode, takes away or gains electrons, and it's produced. Now, in this example, we do have a halogen. A halogen or a halide is a group 7 ion. So in this example, we're not looking at the hydroxide ion. we're going to be looking at the chloride ion. However, what would happen if there wasn't a halogen ion? Let's just say we didn't have Cl minus here. You would actually have oxygen produced. So this slide that you're looking at here, this is kind of the thought process that I would have even myself before I answer a half equation question. Is it molten, or is it half equations and there's going to be in solution, and I'm going to be looking at 4 half equations to then take it down to 2. This slide is the 2 rules that I was just speaking about. So you can pause it here, you can take some notes. I've given you the 2 rules and what that actually means. So pause the video now if you'd like to take these down. Sometimes you see these rules under the title The Effect of Water. The reason being it's the water that is added to your compound to make an aqueous solution. Right, we're now going to do some worked examples. I've written oil rig there. Oil rig stands for oxidation is loss, reduction is gain. So we'll start with molten sodium chloride. Okay, so again, we've got our 2 ions. We're going to have Na plus, Cl minus. Now, to do half equations, you just need to decide what is going to happen to the ions on either side of the equation. Okay, and I've written it like so. So we know that when the sodium ion is going to go to the electrode, and that's what the arrow is kind of representing here, it's going to turn back into sodium. When we look at the chlorine, we see that it is going to go to the electrode and it's going to turn back into Cl2. Okay, so here we are going from the ions and turning them back into atoms. Okay, so let's start with just start with Na plus. Okay, now the Na plus, it is a positive ion, so it means at some point it has lost electrons to become more positive. Okay, now for it to get back to its neutral atom, it needs to get rid of that positive charge. It can only do that by gaining more electrons. So we would say that this ionic equation is going to represent a reduction half equation. So I'll write it as R. Okay, so sodium is going to have electrons added to it. Okay, and you put them on the left-hand side of the equation like so. So it means that you've got your sodium ion there. We're going to have to add electrons to it to take it back to a sodium neutral atom. Now, we've only got 1 plus charge to get rid of, so we only add 1 electron. Now you look at the chlorine. The chlorine was negatively charged and it's turning back into a chlorine diatom. So for it to become, and I'm going to rewrite the equation a little bit there just so I can give myself some more space. So for that chlorine ion to become, let me just rewrite it. So for that chlorine ion to turn into Cl2, for it to turn into chlorine, it had to gain electrons for it to be negatively charged. So if we now want it to be neutrally charged, we are going to want it to lose electrons. And to demonstrate the loss of electrons, we actually add the electrons on the right-hand side. Now, that's quite difficult to remember, and students find it really tricky, which is why I always say, write your reduction equation first, because you're adding electrons and the equation makes sense. You know that the electrons go on the left-hand side. Then do your oxidation half equation where you know the electrons will have to go to the opposite side of where the reduction one is. So for the Cl2, we write the loss of electrons on the right hand side. So that's the beginning of your equation there. But what you now want to do is check that it's balanced. Now, first of all, the number of chlorine isn't. It's Cl little 2. We need a big 2 here to show that there are 2 chlorine ions turning into Cl2 diatom. Now, because there are 2 ions, each with a negative charge, they must lose 2 electrons in total. That is your 2 half equations for the molten sodium chloride. Okay, we've got the R for reduction, the O for the oxidation. Remember, this is showing the loss of electrons, oxidation. This is showing the gain of electrons, reduction. Now we look at sodium chloride solution. So we did have all of these ions at play here, and we said using those rules we are only going to write half equations for our chlorine and our hydrogen. I will start with the positive ion this time. So we're going to have H plus, and it's going to turn into H2. We are going to have Cl minus, and it is going to turn into Cl2. Okay, so let's start with the hydrogen, and you can see just as before, now the sodium was the positive ion. Here the hydrogen is the positive ion, so this will be the reduction half equation, this will be the oxidation half equation. Okay, now again as before, we know that to show the gain of electrons, we write the electrons on this side plus electrons. Now, in terms of how many we need, look at the H2 on the right-hand side. There are 2 of them. We must put a big 2 here. If we've got 2 H plus, we must have 2 electrons to balance that out. And that's your completed half equation for hydrogen. Let's look at chlorine. Chlorine half equation is exactly the same no matter the example that you're looking at. So that by doing practice, you always will come across half equations that are exactly the same. Okay, so this one here is showing you the reduction half equation. This one here is showing you the oxidation half equation. Let's now look at a different example, this time copper sulfate. So you could be asked to describe either molten or a copper sulfate solution. What we'll do is we'll really quickly look at the molten one. So copper sulfate does get split into 2 ions, copper and sulfate. Okay, so looking at the sulfate ions isn't something that you need to do at GCSE in terms of a half equation. You could be expected to do the half equation for copper, however. Okay, we would have Cu2 plus turning into Cu, copper. Okay, it's a positive ion, therefore we know, again based on the previous slide, the positive ions undergo reduction, which is a gain of electrons. So here the copper has got a 2 plus charge. For it to become a 2 plus ion, it at some point must have lost 2 electrons. So therefore, to go back to being neutral, it must regain those electrons. And you write the electrons on the left hand side. Because it's a 2 plus ion, it needs 2 electrons. So that here is the half equation for copper. We don't need to worry about the sulfate one. Now we look at copper sulfate solution. We would have had Cu2 plus, SO4 2 minus. Remember, the solution ions are the ions from water, H plus and OH minus. Let's go through and apply the rules and see which ions are going to need half equations. The rules say that if you have 2 positive ions present, the least reactive ion will be discharged at the electrodes. So 2 positive ions here, copper 2 plus and H plus. Now copper is actually lower than hydrogen in the reactivity series, so we will be doing the half equation for copper. Look at your 2 negative ions. The rule was, if you have 2 negative ions and one of them is a halogen, the halogen will be discharged. If there is not a halogen, then oxygen will be produced. Now we get the oxygen from the hydroxide ion, not the sulfate ion, and that is the one that we'll be doing the half equation for. Now we'll start with our copper, and it is exactly the same as the one above, like so, and we will annotate the fact that it is the reduction half equation. Now we do the oxidation one. The oxidation one is going to be our other ion, which is clearly the hydroxide ion. So we're going to start with OH minus here. We are going to end up with the oxygen that we said. Now, something that you just need to learn by heart here is that the hydroxide ion, not only does it produce oxygen, it also produces water, and that is a fact, and that's something that you have to learn. So now we've got to go through and we've got to try and balance out all of this. Okay, now again, you can go through the process of balancing out either sides. For the purpose of this video and time, you do need 4 hydroxide ions in order to produce everything that here that is on the right hand side. Okay, you'll notice that you've got 4 oxygens. Now there is 2 in the O2, okay, and there is 1 in the O here. With the hydrogens, you've only got 2 here, but you've got 4 over here. So this water will actually have a big 2 in front of it. Now, again, like I said, for the purpose of this video, I'm just going to tell you that that is a fact, and I would always learn that. 4 hydroxides gives you O2 plus 2 H2O. Now we balance out the electrons, okay? Now the water is a byproduct here. It is the oxygen that we want. Look at the hydroxide ion. You've got 4 lots of negative charge. We need to balance that out on the other side with the addition, the loss of 4 electrons. So that is your final one. I know that last one is quite tricky. However, that is always the half equation you're going to use for the production of oxygen. So it's something really, if you're not sure, you can just learn by heart. I'm now going to give you 2 molten examples that we're going to look at. The reason being these are 2 that are commonly used on most GCSE specs in terms of molten examples. So aluminium is Al3+. Again, how do I know that? Or I've known it because I've done lots of these examples, but how would you know that? You would know that by looking at your common ion sheet. Okay, I'm just going to move this up slightly. I'm just going to lower that down. Okay, so aluminium oxide. We've got aluminium. Again, we'll do our 2 equations. Doesn't matter really which one that you start with. We've got Al3+ turning into Al aluminium atom. That is going to be our reduction half equation because it's the positive ion. Our oxidation half equation is going to be O2 minus turning back into O2. Now let's start with aluminium. It has got a 3+ charge, which means that it needs to gain 3 electrons to go back to being a neutral aluminium atom. So we're going to write +3 minus. Now, oxygen. Oxygen has, it's got a 2- charge, and we've got O2, a diatom on the right-hand side. So first of all, let's put in our electrons. If we've got a 2- charge, we're going to have to lose 2 electrons. Remember, we write the loss of electrons, although confusing, as a +2e- on the right-hand side. Now, our electrons are balanced at this point. However, our oxygen atoms aren't. We've got 2 oxygen atoms here, no little 2 here. So we must put a big 2. I've now, however, unbalanced my electrons. I've got 2 lots of 2- charge. That must be balanced out by 4 electrons here. And it would be 4e-. I'll rub out the annotations that I did to make it a bit easier to read. Okay, that's your half equation for molten aluminium oxide. Let's now do molten lead oxide. Lead is Pb2 plus. Oxygen, or the oxide ion, is O2 minus. So again, we will do our two equations, the reduction and the oxidation one. We can do the oxidation one straight away because it's going to be exactly the same. Let's do our Pb2 plus. Pb2 plus is going to turn into Pb. That 2 plus ion must gain 2 electrons to become Pb. Okay, so you can see already the more examples you do, the easier they become. I'm now going to give you an opportunity to do 2 examples yourself. So pause the video now and do these 2 examples. You've got molten lead bromide copper chloride solution. Pause the video if you want to do it. Once you play it again, you will see on the last slide the answers. Good luck.